Hi, welcome to Unit 83. In this unit, we're going to combine some resources from astronomy, from astrophysics, combined with elementary particle physics, to come up with a model of how the universe has started, okay, and where we are right now. So again, oops, let me click in here. Again, we're going to talk about take the current understanding of the expansion of the universe and run the movie backwards. So the universe basically must have been smaller to the point that there was a starting point 13.7 billion years from today where the universe started. Okay. Uh, if we run the models correctly, we should really find a certain ratio of helium that formed from hydrogen to the hydrogen. So the most elementary particle in the universe is hydrogen, and helium would have formed enough, and the ratios are what they are today. So the model is basically correct, at least in terms of this understanding. We're going to explain basically the amount of hydrogen, helium, I should say, versus hydrogen, and then we're going to have a look at a puzzle that is actually bothering elementary particle physicists and also astronomers because of the fact that if we go by what we know elementary particle physics, that basically the vacuum energy, I should say it, the energy in the vacuum causes pairs of matter-antimatter to form all the time. But this must be the same numbers. Except what we see is more matter than antimatter. As a matter of fact, the correct number should be one matter more than antimatter in a billion. If you take a billion processes like this ones, and they form pairs of matter antimatter, one of those pairs end up with more matter than the rest of the antimatter, one in a billion. If that's the case, then we will have more matter in the universe than antimatter. Why is that? It should be the same. Okay, so that's a puzzle. And then we're going to describe an essential process in all of this that must have happened in the beginning of the universe, and that is the inflation of the inflationary stage or the expansion, and that's probably related to the dark energy that we mentioned in some previous units. The current temperature of the universe is something or slightly more than 2 Kelvin. That's the average temperature of the universe. Okay, and granted, some stars are in their cores in the basically millions of degrees, okay, kelvins, but overall the temperature is slightly less than 3 Kelvin. Okay. When the universe was 10 billion years, the temperature dropped actually to 3K. It was around 100K. 100K is super cold, by the way. Remember, water freezes at 273 Kelvin. So that's with 0 degrees Celsius. So 100 Kelvin is a negative number. It's almost negative 200 degrees Celsius. So it's a very cold temperature. Okay. And that's when the universe was about 100 million years old. Okay. And that is the temperature. This is the current models, basically. This is the models that we have. They have been questioned so far by the James Webb because the James Webb is detecting star formations that happen a lot earlier than 100, around those numbers, okay? 100 million years, probably around those times. So again, we really need to revise this understanding. But again, this is the stars now start to coalesce from stars and so on and so forth. So that's the stage from which. Below that, the temperature of the universe was too hot for matter to coalesce into forming stars. But we had clouds in here, okay? Around 400,000 years, the temperature was around 3,000 Kelvin. 3,000 Kelvin and hotter would not allow or at least higher than 3000 Kelvin, would not allow matter to exist in a neutral atom. Basically, you will have a proton and an electron not bound together to form hydrogen, and you will have nucleus of helium, which is called the alpha particle. So you will have an alpha particles and two electrons floating by themselves, not bound together. When the temperature drops to around 3000 Kelvin and cooler, then the atoms start to form. And that is really the first time that the light now, because light was bouncing in and off in here, just like what's happening in the core of the sun. But that's the first lights that we have seen. This is basically the cosmic background radiation. Okay, below that temperature or higher than the temperature, uh, less than that, from 400,000 years when the universe was 400,000 years to about 3 minutes, the temperature went down from a billion Kelvin down to about 3000 Kelvin. And that is the stage basically where atoms are forming. Okay. Below that temperature in here, this is a soup basically of radiation, and there is no atoms that form. Then once when the universe was 1 second, so this is the time when the temperature is that high, protons and protons start to interact with one another in a proton-proton process to form helium. And that is the time basically that the helium formed. It was very fast. There is some traces of lithium at that point, okay? At even higher temperatures, even the protons themselves could not have formed. You have a soup of quarks, basically, and electrons. Those are the most elementary particles that we know exist, okay, with extreme high gamma rays at that point. Below that, we don't know. There is no physics to describe anything below that. So we're looking at the temperature going down, and we're looking at the time increasing on this axis in here. And that is what elementary particle physics is telling us in terms of nuclear processes, chemical processes, and actually star formation later on. So again, the time in seconds, the protons, and this is the abundance, basically, how many of those materials you have in here, okay? And the temperature as it goes higher and higher in here, and what the processes are. Obviously, the protons form first, and then the neutrons are basically... neutrons are not stable by themselves, by the way. They have only about 15 minutes of lifespan. Protons are more stable, okay? But they can be formed. A proton can transform to a neutron through a process of capturing an electron. Okay, but the electrons by themselves are electrons themselves are elementary particles. So immediately after the Big Bang, of course, the temperature was too high even for the protons to form, because of the fact that the protons are not elementary particles, they're made up of quarks. But as the temperature cooled down, quarks are really not, they cannot exist by themselves, at least at low temperatures. At that point, three quarks came together to form protons, and of course the electrons, they're elementary particles as they are by themselves. As the temperature got colder and colder, basically dropped down further, then the proton starts to form heavier helium, hydrogen isotopes, deuteriums, through the processes of fusion, and even those they form helium. So those are basically the models that we have. We looked at a process like this one during the when we studied the sun, and we studied the process basically of what's going on inside the cores of the stars. And this is basically one of the processes that we talked about. That was the proton-proton chains, and that leads to the formation of helium. If we go through this model, we find that the helium should represent about a quarter of all of the matter in the universe. And the other 3/4 basically immediately after that remain protons, remain hydrogen. There are traces of lithium and even heavier elements, but those are extremely negligible. Okay? The next big one is actually lithium, but it's negligible. So in this case, this is what the model is suggesting, and that's exactly what at least population 3 stars are. Those are the stars that formed immediately when it was possible for the stars to form. Again, I mentioned the process that forms pairs of matter and antimatter. And matter and antimatter, they come together and they actually cancel to form two photons. And you have to have two photons, by the way, by conservation of momentum, regular momentum. So in this case, this must happen at extreme high temperature. But as I mentioned before, there was an asymmetry that we don't understand its origin, so that there is more matter abundant in the universe today than antimatter. So antimatter and matter canceled out, and only when the temperature cooled down, canceled out, and only the difference that remained in the form of matter. You and I and the stars and everything else that we see, okay, in the current universe. So that's only the remnant of this annihilation that happened early on. So again, we don't really have an understanding of what's going on at this point, what happened, why that imbalance was so that matter dominated antimatter. Obviously, if we happen to be in a universe where antimatter dominates matter, then we would ask probably that question, why antimatter dominated matter? So that's, again, a moot point at this point. And but there was a difference, definitely. And that difference, as I mentioned at some point, was 1 in a billion, more matter than antimatter. And at the end, that's what remains. All of us are just that imbalance. So again, there was an epoch of inflation. So at the time is 10 to the negative 43 seconds. When do we come up with all of these numbers, by the way, is when we combine our understanding of all of the things that we know from elementary particle physics, from relativity, and we come up with these models. And again, we really don't have physics to explain at least the so-called Planck time or Planck epoch. At that point, we really don't know exactly what's going on at that point. And I think there is a C in the Planck in here. Is it a C? Yeah, that's the name of the guy who came up with a lot of these things in here, at least in terms of black body radiation. So again, we don't have physics to explain what's going on at that time, which is 10 to the negative 43 seconds immediately after the Big Bang. So that's 0 followed by 43, basically zeros and a decimal point at the end. So it's no time at all. And then at 10 to the negative 33 seconds, we have the expansion that happened. And that expansion was an inflation. So the size of the universe would grow big, from the size of a proton to the size of a basketball. Okay? So it's really something big. So that you know, a proton is 10 to the negative 15 meters, and a basketball is a few centimeters, okay? So you go from 10 to the negative 15 down to 10 to the negative 1. So that's a 10 to the power 14 volts, okay? Explosion, really. That's really the time of the explosion. So the Big Bang itself was not an explosion. So that's a time when things happen. And it's this one is they may consider to be. So the explosion happened a little later. In terms of elementary particle force, in terms of forces, basically, we know that there are 4 forces in nature, okay? Gravity, which is super weak, followed by the weak force, and there is a huge gap between them. It's not represented in here. If you think about it, this is 10 to the negative 40 compared to the electromagnetic force, and this is 10 to the negative 6. So this is 10 to the negative 30 something between. So the gravity is a ridiculously small amount compared to the weak force, which is 1,000,000 times weaker than the electromagnetic force, which is about 140 times weaker than the strong force. So the nuclear force that binds proton to proton or neutron to neutron or quark to quark, that force is the strongest, called the strong nuclear force. The force that repels two positive charges or attracts a positive to a negative charges or repel two negative charges, that is the so-called electromagnetism, and that has to do with electricity and magnetism. The weak force is the one that is responsible for radioactive decay, transformation of a neutron to a proton and an electron and a neutrino. That force is weaker than this one by like a factor of a million. When they did the lab, this is the work of Abdus Salam and his peers, when they pushed the temperature higher and higher, these two forces basically exhibit they were unified into a force called the electroweak force. So we were able to replicate this in the lab with the current technology that we have. And the W plus and minus bosons and also the Z boson were discovered at this point in here. So we know that. So the model works. If we push this model further to temperatures that we don't have today, nuclear accelerators that we don't have today, and the model suggests that these two forces, the electroweak force and the strong force, will combine. We think, again, that maybe down the road that these two forces, so this is called the grand unifying theory that combines everything in here, and gravity also ultimately will combine with them through the particle that is extremely hard to find, the graviton, and they become one big force. And that theory is basically physicists are looking for it everywhere, including Einstein. Basically, he passed away trying to get to it, and everybody is basically working through it. He basically had his work on his desk trying to get into the theory of everything. The theory of everything will explain this big force in here that combines the grand unifying theory with the force of gravity to a big one. So again, that's how we arrived to these numbers in here I was mentioning earlier. We don't have any physics to describe what's going on beyond this point. We can't have a physics that goes beyond this point. You would have really conditions similar to the beginning of the universe to get to it. Even the strongest black hole out there, the biggest black hole out there, with the amount of energy it has, it will not be able to get to that point. So you need the entire universe to get it to that point. Okay? So this is the current understanding. Again, the current temperature of the universe is about 2.725 Kelvin. That's the average temperature. What you see in here is actually imbalance from the early universe of the temperature, and this fluctuation in temperature, if you wish, is the one that later on went on to form all of the galaxies along and the galaxies and the voids in the universe. The fluctuations in temperature are so small. Okay, they're a fraction of a Kelvin, so they are not that they're within the margin of error actually. So, and you might think so, that's why we think that the entire universe was at some point in one place and expanded. So that's the roots of the expansion, is this uniformity in the universe. And here it must happen so fast that the universe went from a proton size to at least a basketball size in about 10 to the negative 33 seconds from when it was formed. Okay, again, that also explains the fact that we can't really determine the curvature of a space-time, if it's actually the universe, if it's closed in or it's an open, and all of that is because that expansion made it so hard. Right now, if you stand on the floor, it looks flat, but you and I know that actually that's not flat. That's part of a big sphere, which is the Earth. The reason why it looks so flat because we are so small on that big curvature that we can't tell. I mean, engineers build houses and buildings based on the understanding that the surface is flat. But you and I know that that's not flat because the entire Earth is curved because of the fact that it's bigger, much, much bigger than us. That's the same thing. The entire universe, because of the inflation, really was flattened at this point. It's very hard. That's why we, as another unit, we were talking about the critical density of the universe. and we're measuring basically the critical value, the density of the universe to be very close from the critical density because of the fact that the expansion, the early on expansion that happened, it's called an inflation that really flattened everything, and that really explains that thing. Again, what are its roots at this point is part of an ongoing work. Thank you.